Welcome back, guys, to Learning as a Hobby. In this video, I'm going to do the exercises for section 1B in the Axioms book, Linear Algebra Done Right. So let's jump into the problems. There aren't that many problems in this section, so I basically did all of them, and they're all kind of short, so this video is probably going to be a little bit short because of that. Oops, this is a summary. Okay, so here we go for the exercises. Again, some of these we've done already in other videos, so I'm gonna, kind of go through them a little bit quickly. So question number 1 says prove that negative v is equal to v for every v and v. In other words, prove that v is the additive inverse of negative v. So to do that, we add that thing to negative v and see what happens. So negative v plus negative v is the same thing as -1 times v plus -1 times v. We proved that in that works in the chapter itself. You can factor out the constant -1 using the distributive law, and v plus v is equal to 0 by definition of additive inverse. So -1 times 0 is equal to 0. That's another thing we proved in the chapter itself, and that shows that v is equal to that shows that v is equal to negative v. All you have to do to finish this up is just add the additive inverse of v to both sides of the equation here, and you get that what you want. So that's question number 1. All right, question number 2 says suppose that A is a element of your scalar field, and V is a vector in V, an arbitrary vector in V, and that A times V, the scalar multiplication of A with V, is equal to the 0 vector. They want us to prove that either A is 0 or V is 0. This is another one that we proved in another video, but I'll do it again here. In order to prove this one, I'm using this fact from logic. So this statement is a conditional statement that has the logical form like this: P implies Q or R. But just using some mathematical logic, you can manipulate these formulas algebraically. This is equivalent to this, which is logically equivalent to this, which is logically equivalent to this. So in other words, P implies Q or R is equivalent to P and not Q implies R. So what I can do then is assume, for example, that A is not 0 and that A times V is equal to the 0 vector. And then all I have to do is show that that V is the 0 vector. That proves the theorem. So that's what I'm going to do. All right, so let's assume our hypothesis P and not Q. So let the A times V equal the 0 vector and A not 0. Then A times V equals 0 implies that, so if A is not 0, you can divide both sides by, or multiply both sides by the multiplicative inverse of A. So 1 over A times AV is the same thing as 1 times V, and 1 over A times the 0 vector is equal to the 0 vector from, one of the theorems that in the chapter. And 1 times V by the vector space axioms is equal to V. So that shows that V is 0, and that proves the theorem. All right, so that's question number 2. Question number 3 says, suppose that V and W are vectors in V. Explain why there exists a unique X in V such that V plus 3X equals W. And the reason for that is you can solve explicitly for X. So there's only one solution to that equation. All right, so just use your vector space axioms to solve for X. All right, question number 4. The empty set is not a vector space. The empty set fails to satisfy only one requirement listed in 119, which is 119 is the definition of vector space. So where he goes over the axioms and everything. So which one does the empty set fail? And the one that it fails is the fact that there's no additive identity because there's nothing in the empty set. So therefore, the empty set is not a vector space. Right, like I said, these problems are kind of quick, so this video is probably going to be like 5 minutes long. But anyway, we're almost done there. I think there's 2 questions left. Number 5, show that in the definition of a vector space, 119, the additive inverse condition can be replaced with the condition that 0v equals 0 for all v in V. So we can do that here. So let it be the case that 0 times v is equal to 0 vector for all v and v. Then 0, the 0 vector is the same thing as, by the hypothesis, 0 times v, which is the same thing as 1 plus minus 1 times v. That's, just by definition of additive inverse in the base field. And then you can use the distributive law. So that's the same thing as 1 times v plus minus 1 times v, which is, so 1 times v is equal to v by the axioms, but that gives you that v plus -1v is equal to the 0 vector. Therefore, for any v in v, there exists a vector -1 times v, which we could call w in v, such that v plus w equals 0. So in other words, every vector has an additive inverse, right? So they're actually equivalent. Those you can replace one axiom with the other, and it doesn't change the set of things that are in the vector space. So that's probably, what was that, number 5? Number 6 has a long description to get to the problem, but the once you figure out what axiom fails, then it's relatively quick to do the answer. But let's read through the problem here. So I think this is the last problem that I did in this section. So let infinity and negative infinity denote two distinct objects, neither of which is in R. Define an addition and scalar multiplication on R union infinity union negative infinity. As you can guess from the notation, specifically the sum and product of two real numbers is as usual, so define in the usual way. And for any real number t, define for example, t times infinity to be given by this definition. So t times infinity is negative infinity if t is negative, it's 0 if t is 0, and infinity if t is greater than 0. T times minus infinity is infinity if t is less than 0, 0 if t is 0, and negative infinity if t is greater than 0. T plus infinity is the same thing as infinity plus t, which is infinity. T plus minus infinity is the same thing as minus infinity plus t is equal to minus infinity. Infinity plus infinity is infinity. Minus infinity plus minus infinity is minus infinity. And infinity plus minus infinity equals 0. Now, you may recognize that these are not the usual ways that infinity works, for example, in analysis, but these are definitions. So we're defining a set here with two formal objects that we're calling infinity and minus infinity. And the way that the vector space, the operations, I should say vector space operations, because this actually is not a vector space. The way that those operations work, we're defining here. All right, so the question is that set a vector space over R? And they want us to explain. The answer is no, and one of the reasons is that addition is not associative. Other of the axioms might fail as well, but this is the one that I figured out first. So addition is not associative. So for example, if you look at infinity plus infinity and then add minus infinity to it, that gives you infinity plus minus infinity, just using the definitions, right? Which is defined to be 0. Whereas if you do infinity plus minus infinity, you get infinity plus 0, and that's equal to infinity. And notice that these two things are not equal. So therefore, addition is not associative. So therefore, this can't be a vector space because it doesn't satisfy the definition of a vector space. Right, and that's actually, believe it or not, the last problem in that section. So like I said, it's a relatively short section there. So let me stop the screen share. We do have the holidays coming up relatively soon, and this is going to be a particularly busy week for me at work. So I don't know whether or not I'm going to have time to post another video this week, or until after the Christmas holiday. So let me just wish you guys happy holidays, whatever it is that you celebrate. And I hope you enjoy your little vacation, that if you get one over the holidays. And I'll probably see you on the other side, and I guess we'll end up starting back up after the holidays with Spivak chapter, what are we up to? Chapter 4. So we'll start up with Spivak after the holidays. So I'll see you guys then. And in the interim, I hope you guys pick up some good reading for the holidays and keep learning.